In this particular scenario, you're supplied with a project network. Now, if you have the note frames, you have the network in its entirety, but look carefully. If you are using the first edition of Simpson and Hancock, they left an arrow out of this particular scenario. It doesn't mean that you have to print out the note frames or anything, but in your book, what you will want to do is draw an arrow or an arc between F pointing at G. That completes the illustration. Anyway, what are we supposed to do with this illustration? Well, it just starts asking questions. What is the critical path through this network? Oh, all right, well, we're going to have to find the early start, early finish, and the late start, late finish times to determine that. Well, we find early start, early finish times by beginning at the starting node. Each activity associated with the start has an early start time of 0. Okay, well, in the case of A, 0 plus 1, the earliest it could finish is in 1 day, 1 hour. Does it even say? No, doesn't even say. Okay, B, 0 plus 4, 4. The earliest it could be finished in, let's call it 4 days. All right, let's see. E and C can't start until A finishes. I'm just reading this diagram. That means that A could finish at the earliest in 1 day. E, 1 plus 7, it could start at the earliest in 1 day, but wouldn't be finished at the earliest until 8 days. The same thing with C. It could start at the earliest in 1 day, passing that number forward. 1 plus 2 could finish at the earliest in 3 days. I'm using arithmetic. Remember, early finish is just early start plus the task time. Okay, down here, D. Let's see, D can't start until B finishes. That's what the network's telling me, so I can pass that number forward. D could start at the earliest in 4 days. 4 plus 2, it could end at the earliest in 6 days. Now I've got to work my way towards the finishing node here. Let me think. Okay, F cannot start until C finishes, so there's another case I can just pass the number forward. Will finish at the earliest in 3 days. That means F could start at the earliest in 3 days. 3 plus 1 is 4. Let's see, likewise, oh, wait a minute, G. Right, G, where if you have the first edition of Simpson and Hancock, that arrow is missing. Go ahead and put it in. G cannot start until F, that arrow, and D finish. Now, F can finish at the earliest in 4 days. D can finish at the earliest in 6 days. Therefore, what is the earliest that G can start? We have to pick the larger, 6. Because it's waiting on both of them, okay, and then that will finish up at the earliest in 6 days. Let's see, 6 plus 2 is 8. That means G could finish up at the earliest in 8 days. How about, oh, and wait, and that is known as the early start time rule. The early start time of any activity is equal to the largest of the early finish times of all activities that precede it. This was just the first task we came across, the first activity that had more than one activity preceding it, so we had to check, pick the largest. All right, now we have to fill in the rest of these. Let's see, H. H only has one task preceding it. I'm tracing one arrow back, and that's back to D again. That means that 6 gets passed to here as well. H could start at the earliest in 6 days. 6 plus 3 is 9. H could finish at the earliest in 9 days. Now here's another case where an activity, I, has more than one immediate predecessor, right? Tracing arrows back. Now, let's see, G could finish at the earliest in 8 days. H could finish at the earliest in 9 days. Therefore, what is the earliest that I could start? I always pick the larger. Well, it could start at the earliest in 9 days. 9 plus 1 is 10. And then we have one last one to do, and that's task J. And it also has 2 immediate predecessors, one of which will finish at the earliest in 8 days. The other one which will finish at the earliest in 10 days. What's the earliest it could start? Pick the larger, 10. 10 plus 1. The earliest that the task called J is 11. Now, at this point, Actually, ironically, at this point, we could answer the second question in this scenario, but not the first one. Do you notice that the second question is, what is the completion time of this project? We can tell that as soon as we've done the early start, early finish times, because we go to the finish node, we look at everyone who is attached to pointing to the finish node. This network, that's pretty simple, it's only J, and we say, okay, fine, what's the earliest that J could finish? 11 days, I guess. Fine, that's the completion time of the project. The earliest that J is going to be like the last task that's done. The earliest it can be finished is the earliest you can be finished with the project, and we assume that you want to do it as soon as possible. Therefore, that's the completion time of the project. So I'm skipping a question, but we might as well fill it in. 11. Okay, now wait. He said, yeah, but we're supposed to be working on what's the critical path through the project. Okay, in order to determine that, now we have to find the late start, late finish times. We have to begin at the finish node, and we have to work our way backwards. We begin at the finish by noting this fact that we expect this to be done at 11 days. Okay? That means that anybody connected to the finish, which is just J, that just became their late finish time. That is the latest we will tolerate finishing them, in 11 days. Okay, 11 minus 1 is 10. That means the latest we could start J without creating any delays is 10 days from now. Right, that was just a little bit of arithmetic. Late start equals late finish minus the task time. But anyway, now we back our way up through the story of the project. J has to start at the latest 10 days from now. It can't start until E and I finish, so pass that number back. They have both, at the latest, got to finish up in 10 days. Now in the case of I, 10 minus 1 is 9. The late start time for task I is 9. In the case of E, 10 minus 7 is 3. The late start time for task E is 3. All right, now we want to just keep backing up through the network. I'm looking at I right here. I has to start at the latest 9 days from now, but it can't start, trace the arrows back, until G and H finish. That becomes their new deadline. The late finish time for H is 9. The late finish time for G is 9. Now the arithmetic, 9 minus 3. Okay, H has got to start at the latest 6 days from now. In the case of G, 9 minus 2, 7. G has got to start at the latest 7 days from now. Oh, okay. Well, talking about G, G can't start until H and D finish, right? Okay. Well, G has got to start at the latest 7 days from now. That means that for a fact, H has got to finish up 7 days from now. 7 minus 1 is 6. Oh, and I might as well follow this thread since it's a nice, neat little chain here. F can't start until C finishes, right? So see, nice, neat little chain. You can just pass that number back. That means C's got to finish at the latest in 6 days. 6 minus 2 is 4. C's got to start at the latest in 4 days. And actually, following the chain back, I come to A. Oh, a task like A, we have to take a little more carefully, because let's look at where we are. A must finish before C and E start. I'm just looking at the shape of the network. Okay, now we know something about C and E. We know that C has to start at the latest in 4 days, and we know that E has to start at the latest in 3 days. Neither one of them can start until A finishes. Therefore, what's the latest that A could finish without creating any trouble? Now we pick the smallest. Well, it would have to be finished in 3 days, because if it wasn't, that will mess with E. Okay, that's the late finish time for A. 3 minus 1 means the late start time for A is 2. Oh, so A, at the earliest, we have the option of starting on it right now, time 0, or we could wait as late as 2 days from now and theoretically not mess up the on-time completion of this project. Now, that reasoning that we did to get the late finish time for A, that's known as the late finish time rule. The late finish time for an activity is equal to the smallest of all the late start times of the activities that follow it, immediately follow it. Oh, okay. Oh, and we're going to, I do believe, yeah, we need that rule again for D, because D has 2 tasks following it, okay? G and H cannot get started till D finishes. G has to start at the latest in 7 days, and H has to start at the latest in 6 days. We pick the smaller of the 2, that's the 6. That becomes D's deadline. It's got to finish at the latest in 6 days. 6 minus 2 is 4. Okay, that's the late start time for D. And then actually we can just pass that number back because D is waiting on B to finish. So the latest that B can finish without creating problems is 4 days. And then 4 minus 4 is 0. I'm really glad to see that 0. The late start time of 0 of somebody at the starting node. Because I'm looking for the critical path, right? And the critical path is a set of all activities with 0 slack, which is the difference between late start and early start, or late finish and early finish. And we can see it on the diagram now because that's going to be the where is it? That's going to be all the activities in which those timings match. We got the same answer each time, like B. 0, 4. D, 4, 6, let's see, not in here, they don't match. Oh, H, I, and J. Now, what I did was highlighted all the activities with 0 slack. Now, I want to check that that's indeed a path. A path is any route from the start to the finish. And does this make sense? Is it a route? Well, from the start you can go to B, and from B you can go to D, and from D you can go to H, H to I to J, J to... Yes, it's a path. We found it. The critical path through the network is B, D, H, I, and J. Answered that question. All right, next question. What is the slack in activity A? We were just saying slack is the difference between, for instance, the late finish and the early finish, or the late start and the early start. You'd better get the same answer in both cases, because if you don't, there's some kind of problem with your math. So we look up here to A. Let's see, late start time of 2. Yeah, I was commenting on that. Early start time of 0 equals 2. There's a slack of 2. Versus, those are the start times, excuse me. Versus, you'll get the same thing if you use the finish times. Finish times. Okay, these are the F's. Late finish time of 3, early finish time of 1, same old 2, gets you the same answer either way. All right, so that's really simple to answer. Those are F's, those are F's, those are S's. What else do we need to know about this? We're moving through the questions. We come to, oh good, the last one. All tasks longer than 1 day can be crashed to as little as 1 day, although prices vary. Task B costs $600 per day to crash, while task H costs $200 per day, and all other eligible tasks cost $100 per day. Which tasks should be crashed to shorten the project to 8 days? How much will this cost? Oh, unlike the last couple questions, this is not going to be so fast. Right now, the project takes 11 days, right? That was the answer to one of our questions. What this question is asking is, how do you shorten the project or crash it, right, to 8 days? The first thing we have to remember is we shorten a project from 11 to 8 days by shortening it 1 day at a time. With crashing, it doesn't matter whether you're cutting it from 500 to 250 days. You want to shorten it 1 day at a time. Oh, okay. Well, then we'll do that. The other thing that we need to remember about shortening or crashing a project is you shorten a project by shortening its longest path or paths. Oh, wait, and longest path. What's another term for the longest path through a network? The critical path. So you're probably thinking, oh, I get it. We're going to, what was it? Shorten B, D, H, I, J. Yes, actually we are, but it's not yeah, it's not that simple. Here's what we need to do. To crash this project, the first thing we need to do is we need a list of all of its paths, all of them. Okay, all paths. We know what one of them is, right? One of them is B. I'll just go ahead and copy that one. B, D, H, I, and J. And let's see, these are the paths. Really what would be handy here is to have a worksheet that then also tells me the lengths. For instance, I know that the length of BDHIJ is 11 days because the length of the critical path is the length of the project. And we've already been there. We know the project's 11 days long. If you look, though, at this diagram, there are 3 other paths. A path is any route from start to finish, and I see 3 other ones. There is, for instance, this route. Begin at the start, go to A, go to E, and go to J, and from J you can get to the finish. That's another path. So I need to note that A, E to J is a path, and oh, by the way, that path is, if you add up the length of A, E, and J, 9 days long. And I need to know that. Okay, then who else? Well, if you look, here's another path. From A to C to F to G to I to J. That particular path, I added up 1 plus 2 plus 1 plus 2 plus 1 plus 1. I got 8 days long. And then finally, there's another path that starts with B, from B to D to G to I to J. That particular path, B to D to I to J, I get is 10 days long when you add up the duration. You know, that's going up through here and then to the finish. You say, well, yeah, okay, fine. Now what? In order to figure out how to get this project done in 8 days, we must first figure out how to get it done in 10 days. Or what's the best way to get it done in 10 days? 10 days. It's going to naturally take 11 days because its longest path is 11 days long. I want to first knock it down to 10 days. In order to do that, I need to look at the least expensive way, right, of shortening that one path that's 11 days long, that's making it 11 days, down to 10 days. Okay, well, if I were to shorten any one of these tasks along that path, that would shorten the path. So I could shorten B, D, H, I, J. Well, wait a minute. Have to be careful. Some of them are 1 day long, like I and J. They can't get any shorter. Oh, really? So actually, my candidates are right in here, B, D, and H. Okay, well then who would be the least expensive? Oh, B is really expensive. B's a $600 one, right? And wouldn't you know it, H is $200. Okay, well those are the 2 expensive ones. That means that, now wait a minute, that means that D, I could shorten D and it's cheaper than the other 2, right? Because it falls in the category of just all the other ones, which are $100 per day. Okay, so I just made my first decision. My first decision, right, is shorten D for $100. Now, what's that going to do? Well, that's going to knock this from 11 days to 10 days, right? Because we shortened it up by a day. And notice this. This is why we really need a list of tasks. It's going to do the same thing down here. Oh, that's nice. The project's still 10 days long at this point, but this particular path is now 9 days in length. Ah, all right. Now, you say, okay, but we don't want it to be 10 days long. We want it to be 8 days long. Right. Now what we do, that it's 10 days long, is let's figure out the least expensive way to shorten it to 9 days long, 1 day at a time. Okay, 9 days long. Well, BDHIJ is still the problem. It's 10 days long. So really what I'm now looking at is what is the cheapest, the least expensive way of shortening this again so that it's 9 days long. Now, in the case of D, we have to consult. How long was D to start with? D's right there. Oh, D's was originally 2 days long. And what we've just done is we've shortened it by 1 day, so now it's 1 day long. That's why we can't shorten it again. And that's an important feature of this problem, because it said that they could be as little as 1 day, but no shorter than that. So basically, as far as crashing as an option, this activity called D is exhausted. Okay. Oh, which means we're only left with B and with H. Okay, we didn't like either of them last time because they were more expensive than D, but now we can't use D again. So which one's the lesser of two evils? H is less expensive than B, so that'll be our next decision, is let's shorten H. And H is just on that path. Okay. That means that that path is now 9 days long. Funny, this path is 9 days long, and this path is 9 days long as well. But that's okay. The project is now 9 days in length. I better note my decision, though. Next thing we want to do is shorten H for, what is it, $200? Now, at this point, the project's 9 days long. Maybe I'll just note that. Whereas the result of step 1 was that at least we got it down to 10 days. And then this is the situation that we're in. Oh boy. Now what? Now we have to figure out the least expensive way to get these paths down to no more than 8 days long. And this is what tends to happen in crashing. As you squeeze the project, the paths start to pile up, so to speak. I need a solution that will shorten this path and that one and this one. 3 out of the 4 paths. Well, I can shorten more than one activity, but the question is which ones do I want to shorten? Well, first off, let's see. Is there anything left in H? Yes, H was originally 3 days. So H is down to 2 days. So I could shorten H again. The reason that I'm looking at H is because I know that we have to shorten this path, B, D, H. And I know that B is a lot more expensive. B is a lot more expensive. But B is on more than one path. So I'm wondering if I shorten H to justify shortening it and not shortening B, I need to make sure there's a way to shorten this path as well, that the combined cost isn't more than that $600. Oh, okay. Well, to shorten that path, the I and the J don't count. They're 1 day long anyway. So the only thing left is G. And, oh, wait, G. G will work. G is only $100. And then this is $200. That's much better than the $600 to just do B, but that would benefit both paths. So I'm already seeing a strategy here. Let's shorten H again for $200 and G. G's inexpensive, $100. Now wait, H, that will knock this down to 8. That's great. And G will shorten both these paths. This one didn't need to be shortened, but it got shortened. It's down to 7. This is down to 8. That's great. My only problem then is A, E, J. J can't be shortened. A can't be shortened because it's 1 day long. I'm hoping that E can be shortened because, oh yeah, E is really long. E, that's our only answer in that case. I'm going to have to sort of add it to the bill, and E. At least it's one of the less expensive ones, $100. Right? Then that one, now 8, 8, 7, 8. Perfect. There's the plan. What we want to do is essentially shorten D by 1 day, shorten H by 2 days, shorten G by 1 day, shorten E by 1 day. It asks for the cost. That's the plan. That will get us down to 8 days. The cost is just tallying this. Let's see, we spent 100 plus 200 is 300 plus another 200 is 500, 600, 700 to spend $700 total in crushing.